This is the CMS detector, and Brown University is collaborating here with, we have many graduate students. So this is an international collaboration with many different countries participating. US has a fairly big role in terms of the design and the building of this detector. Our group at Brown University has participated in building the part of the tracker, as well as we are collaborating with the hadron calorimeter part, which is the outer part of the detector. The tracker is one of the inner parts of the detector, which goes right above the beam pipe. The beam pipe is this long pipe that you see through which the protons come in and collide at the center of the detector. There is people are working there currently in preparing the area so that the innermost part of the detector, which is called the pixel detector, just like your camera has pixels and digitizes the image, then you put all of those together, each pixel together, to make a photograph. The same way, when the particles collide at the center of the beam pipe, the protons collide and other particles come out, we try to image these particles as they are coming out of the collisions which happens between protons head-on and right at the center. So as the particles come on, we come out of and fly out of the detectors, we try to image them by taking photos with different types of detectors, and different types of detectors take photographs of different characteristics of the particles. The detectors are not just one big detector, but there are lots of different parts of the detector, pieces of the detector. It's like an onion which has various layers. So the first layer is the pixel detector, and the second layer is the silicon tracking device, globally speaking. And so as the particles which are produced in the collision, how they travel outwards is really recorded very precisely by the pixel detectors and the silicon tracking detectors. And these detectors are sitting inside the magnetic field. So how these particles curve inside the detector give us a measurement of the momentum and energy, and the way they curve give us an idea about the charge of the particle. So some of these particles which are produced in the collision actually do not decay right away, and if you try to reconstruct their path through the detector, they don't point back to the collision point, but at a point which is displaced or sideways from the collision point. This is because they are long-lived particles that decay after flying a certain amount of time, and we could use those characteristics of those particles to pinpoint what type of particle was being produced. And one of such particle is the B quark, and me and my group are studying the properties of the B quark, trying to understand how the B quarks will look like in our detector, how to identify them, because many of the theories which try to tell us about the origin of the mass have B quarks in the final state. Our group is also involved in the calorimeter, which sits outside, which catches the total energy of the particle, and the outermost calorimeter is called the hadron calorimeter. Our group is, our students and postdocs are involved in helping build it, helping understand how it functions, and then write the software to reconstruct the particles which will be seen by the detector and measure its energy.